It's a pleasure to welcome our speaker in the SMRI Algebra and Geometry online seminar today, who's Hankyung Ko from Uppsala University. And she's going to tell us about joint work with Ben Elias, a singular Coxeter presentation.
Okay, thank you for the introduction and thanks a lot for invitation. It's a pleasure to talk here. So the title was given and we'll start with defining Coxeter groups. And when I say Coxeter group, I mean it's a group with a fixed presentation called the Coxeter presentation. So a Coxeter presentation of a group is a presentation by generators and relations of a specific form. So what form is it? We have a generating set, and I will denote the generating set by S and the group by W. And we assume S to be a finite set. And the generators satisfy the following relations. The first is the braid relation. So given two elements S and T, we have this relation. So if you multiply ST alternatingly and starting with T, and you do it M times, then starting with S and multiplying M times is the same as starting with T and multiplying M times. So this number, it's same for STTS, of course. M is part of the presentation. And we do allow M to be infinity, and in that case, there is no relation between S and T. Another class of relations is the reflection relation, which is S times S is the identity element. The identity element will be denoted by E. And this holds for every element in the generating set S. Okay, so the presentation can be recovered from these numbers, integers, MSP. So this is the definition. And if I will later I will just say Coxeter group. That's when I say it, that means it's a group W and generating set S with this braid relations, fixed and reflection relation. And the probably most famous example of Coxeter groups is the symmetric groups. A symmetric group is a group of permutations of a set, say the numbers from 1 to n plus 1. And to get the Coxeter presentation, we take the transpositions of two adjacent numbers. So let Si be the permutation, switching I and I plus 1 and fixing the rest, and they will generate the group. And they satisfy the desired relations, the braid relation, when I and I plus 1. So when two generators are involving some common number, then we have this braid relation with M3. And if I and J are far, then they are involving different numbers, so they commute. And these are reflections, so they satisfy the reflection relation. Okay, so another example which will appear many times in this talk is the affine symmetric group. And here we have 3 generators, and for any pair, any 2 of them, the M is 3. And now I will just show you this picture, and later, quite soon, I think I will explain what it means, but you can guess probably. And another example is the Dietary Groups. So this is when the generating set S consists of 2 elements denoted by S and T. And in this case, we have only two generators, so the presentation is determined by one integer, m. And a common notation for diagonal groups is this I to m. And the resulting group W is the symmetry group of polygon with m edges. So for example, if m is 4, we have a square, and the group is the consists of the symmetries of this square, and we can take the generators. So we want them to be reflections. So we take two reflections that are next to each other, then it satisfies, in this case, the braid relation ST equal to TS. And for M5, you have a polygon with 5 edges, and S and T generate and satisfy braid relation. Okay, so now I want to introduce some notions associated to Coxeter presentation, WS. So first, W is a group generated by S. So every element in W is a product of some elements in S. And the way we write it is called an expression. I think it's a common term. So an expression of an element W is a string S1, S2 to SR in S, so that W is the product. And we can define the length function to be the smallest number of letters, or the shortest, the smallest number of letters that appear in an expression of W. Okay, now we can say when an expression is called reduced. So this is the shortest, the reduced expressions of W are the shortest expressions that expresses W. So if this length of the string agrees with the length of the element. And we can use this to define the broad order. So in broad order, W is less than X if W has a reduced expression, which is a sub-expression of a reduced expression of X. And this agrees with the broad order coming from geometry. And some fact about finite Coxeter group is that if we have a finite Coxeter group, then we have a unique maximal element, and I will denote it by W0. And this is also the unique longest element. And another fact is that we know our Coxeter, finite Coxeter groups. There is this ABC classification. And type A is the symmetric groups, and I2 was the dietary groups. Others were not defined. Okay, so to illustrate these definitions, so let's take the M3 case in the dihedral group. So this is, we have this right triangle, and we have this reflection S and reflection T. So this was how we present the group. The symmetries are generated by S and T, like here, and they satisfy the relation STS equal to TST. And we can take this region which I name E, because if we start, if you look at here and keep track of it when you act by some element in the group, and if you act this by the identity element, it will be there. And if you act by the reflection S, it will be mapped to where I wrote S. And the element ST act on E to map it in this place. And another way to get here is to start from the left and act on the right. So I draw this line here, and this line correspond to, or segment correspond to T. And when you cross this, you multiply T on the right. And it's the same because you reflected the original hyperplane corresponding to T along the where this S is, it multiplying on the right with T is same as reflecting here. And you can get other elements. STS is after crossing the S facet, and you can go back to E and you multiply T. That's like crossing this segment, and then you cross S and you cross T. And that's where you have the longest element. And if you multiply more things, you will get a non-reduced expression and go backward. So what I wrote are reduced expressions, and the lengths, because we have reduced expression, the lengths are the lengths of the expressions exactly. So lengths are 0 for E and 1 for T and S. SST has length 2 and the longest has length 3. And here is the Brouillard order. Okay, now I'm back to the slide. So now I can give this example using the same way to get elements by acting with the reflections. So this was the affine symmetric group S3 tilde, and here I chose this to be the origin. And if you cross red line, you multiply S on the right, and you cross green line, you multiply U because it's green on the right, and so on. So these are some of the reduced expressions here, and the old expressions are unique reduced expression of the element, and the rest have a different, more than what's written could be a reduced expression. So, for example, here. Okay, and I now can talk about braid relations in relation to reduced expression. So I want to reformulate very slightly the definition of a reduced expression. And here I directly define reduced expression, not by defining expression and then reduce. So a reduced expression of an element W is a string such that it expresses W and such that the lengths add. So these are all 1. And that means the right-hand side is R, and this element is W, and that was the original definition. And yes, I define it this way to make parallel to something that will come later. So we take this as the definition. And the theorem of Matsumoto, where I heard it's a theorem of Tit, but it's called Matsumoto's theorem. It says that any two reduced expressions of an element W are related by braid relation. So a priori, if you have two reduced expressions or two expressions, we have a presentation that means they are related by braid relations and reflection relations. And this says that we do not need to apply any reflection relation in any direction if you have reduced expressions. So this is a very important and extremely useful fact. And so it feels a bit wrong to say applications, but I just wrote a few things, and this cellular basis of the Hecke category, if I have time later, I might say something about this. Okay, so an example to illustrate Matsumoto's theorem. And then here I want to go one rank up than before to give the symmetric group on 4 letters. And it has 3 generators, STU. And what I drew here is what's called the thinking diagram. So you write the generators as vertices, and if the braid relation between them has number 3, then you draw an edge. And there is so S and U commute, and there is no direct edge between S and U. So that was what this diagram means. And we take the longest element in this group. It has length 6. And what's here are all reduced expressions of this element. And one example is STS, UTS. And to get other reduced expressions, as Matsumoto's theorem says, you can only apply the braid relation and get everything. So here you have STS equal to TST, and that was the black one. So I drew black and so on. So in general, if you have an element and you write down all the reduced expressions and connect them using these edges, the graph will be connected because of Matsumoto's theorem. And we here use braid relations only. Okay, so now I have parabolic double coset. And I need first to say what a parabolic subgroup is. So WS is a Coxeter system. And you take a subset in the generating set S, and you consider the subgroup of W generated by this subset I. Then this Wi is again a Coxeter group generated by this set I. And this is very easy. You have the same MST and same braid relation, same reflection relation, everything restricted. And for example, if W was a symmetric group Sn, then any parabolic subgroup, so these are called parabolic subgroups, they have the form, it's product of small symmetric groups. Okay, and we say a subset I in S is finitary if the subgroup, the parabolic subgroup generated by it is finite. And this will be an important restriction for us. And as noted before, since it's finite, it has a longest element and it will be denoted by W sub I. And now I can talk about the cosets. So let's take two finitary subsets of S, and we will consider P, which is some double coset with respect to this parabolic subgroup generated by I and parabolic subgroup generated by J. So this is the usual definition and notation, and I will use the letter P to denote this. And the fact is that similarly to when you have a finite Coxeter group, this double coset contains a unique maxima element, which will be denoted as overline, and they contain a unique minima element, which I denote by underline. Okay, now I give an example and I can already explain the main idea of the what will come in the second part in this example. So let us take W to be the symmetric group S3 with generators S and T. And here everything's finite, so every subset of S is a finitary subset. We have 4 of them, MT, ST, and ST. And for now, we consider the double coset, which are actually left coset, is maybe right coset. So on the left, you have empty set, the parabolic subgroup generated by empty is the trivial group. So this double coset is the same as a single set. And in this picture, so these two-dimensional faces were the elements of the group, and we can assign these one-dimensional facets, double cosets, where J has one element, and we have another double coset here, which has J equal to ST. And when I write this kind of set, I will just list the element without the set sign. So if we do this, then so this is what we saw before. So you start here, and we crossed S, crossed P, and crossed S to get to SDS, which was the longest element. But since now we have these one-dimensional cells, we can split this into more steps. You go into this facet, go out, go in, out, and same for this other S. So the braid relation identified this path and this path. But note that we have also this coset, so we can go there. So instead of going from here 2, 3, 4, 5, we can go from here to here and out. And if you like, you can continue. So there are these extra operation or movements you can make. So to repeat, this was the braid relation, and now it is divided into 4 more local relations. And this is, I think, yeah, or this is the idea for the singular presentation. So instead of this big relation that was regular, that comes from the regular Coxeter group, we have more relations, but they are smaller, and it's not maybe so clear here, but they come from a similar set of relations by putting it in the correct places. Okay, so I cannot see the is there a question so far? And I here, yeah, for now I only talked about empty, J cosets. But if you want to consider, for example, T here, so multiplying T on the left correspond to reflecting along this original hyperplane. So if you take this one, and if you had a T comma S coset containing E, that will be ES TS. So it's a collection of the facets here, and yeah, there is a similar description if you restrict this complex to some area, and it will be in more general form, and more formal form come in the second part of the talk. So yeah, I think it's a bit early. So yeah, so the rest of the talk will be to generalize this idea, and to make it easy to write down, to say, I need to introduce the Coxeter monoids. So given the data defining a Coxeter group, it can define some other algebraic structures, and one of them is the Coxeter monoid. So yeah, another thing that I'm not going to define that comes from a Coxeter presentation is the Hecke algebra, but here I define the Coxeter monoid. So the Coxeter monoid is a monoid, which means it has a associative operation and the identity element, but not inverses. It has a presentation, Coxeter presentation, where the generating set is S, and we have the same braid relation as in the Coxeter group. But to distinguish Coxeter monoid and Coxeter group, I will write star to denote the product. So on the left, you start with S, on the right, you start with T, and you multiply M of the m elements, and they are the same. So it's exactly the same braid relation. And the quadratic relation, or the reflection relation, is replaced by this quadratic relation, which I call the star quadratic. And if you multiply S with S, you get S instead of E. And this is actually what's quite useful in studying something called the Hecke category, which is the main motivation for me and for my collaborator to do this presentation. And to make maybe another remark, why this might be useful is that in let's look here in this example. So let me just contrast to the Coxeter group and Coxeter monoid in terms of the paths in such a complex. So in the Coxeter group, in this picture we only went forward, but for example, let's say I multiply S, so we are back to the regular case. And if I multiply again, I go back. If I multiply T, I go forward. So in the Coxeter group, depending on whether when you multiply something, depending on whether it's reduced or not, you either go forward or go backward. And in the Coxeter monoid, if you multiply, so because of this relation S times S is S, you either go forward if you multiply in a reduced way, and if you multiply something that makes it not reduced, you stay. And so it only goes forward or not. It doesn't go. So that's the way. So later we will do things with this path and this Coxeter monoid. This kind of presentation is suitable for what the kind of path that we will consider.
Thanks.
So now I can introduce the expressions in the singular word. And the parabolic expressions, singular expressions are, I think, both good names, but maybe not perfect names. But I call it a singular expression. So, and I just call it expression. It will be clear. So an expression is a string, and this time instead of taking elements in S, we take subsets in S, and we require finitary. This is important. So it's a string of finitary subset of S, and there is a condition. So either of the two conditions should be satisfied. Either when you so in two subsets next to each other. So how do it? So either you remove one from the previous step, and I will express this in a notation where I just write minus S, or you add an element that was not there before, and I write plus S. So in other words, every two pair that's next to each other differ by one element everywhere. So that's what an expression is. And here is an example. So empty set is a parabolic, is a subset of S, always finitary. And if you take some S in S, it's also always finitary, and you can take S as the second one, and you remove S and add T, remove T, add S, remove S, add U, remove U, add T, remove T, add S, remove S. And if I write down what I said when I was reading this, we get this additive notation. So we record the differences at each step. And you have to record where you start. So I will say soon why I call it a regular example. And here are just some other examples. And this is in the notation where I write the subsets, and this is the notation where I write the differences. Okay, so I defined an expression, but I didn't define it as an expression of something. So expression should be an expression of something. And so what is it? What does it express actually? And to say this, to answer this question, I need the Coxeter monoid, and that was why I introduced it. So if you have an expression I flat, then to get what it expresses, so it expresses a parabolic double coset, and to determine this parabolic double coset, you take the product of the respective longest elements in the parabolic subgroups generated by these subsets, and you product them, you multiply them in the Coxeter monoid. And you take this element and take the parabolic double coset, and you started with I0. So that's the subgroup on the group on the left, and the parabolic subgroup corresponding to I sub r is the subgroup on the right, and that's the parabolic double coset P that is expressed by the expression. And this, so I wrote P bar or overline P here, and this is compatible with what I said about longest element. So if you take this product and get the parabolic double coset, then this element is the longest element, the unique maximal element in this parabolic double coset. And when we have an expression, I will use this symbol to say that I express is P, and I use it in both directions. So this is my notation. And let's look at an example. So this is the symmetric group S4 with 3 generators. And consider this expression that we saw before. So if you want to compute what it expresses, you take this this product in the Coxeter monoid, and the longest element in the subgroup generated by MT is the identity element. Here you have S, so E, T, E, S, E, U, E, T, E, S, E, and if you multiply them in the Coxeter monoid, where in the Coxeter monoid, maybe I should have said this, the reduced expressions are exactly the same as the Coxeter group. And then, so this product actually don't depend whether we are in the Coxeter monoid or in the Coxeter group. And anyway, if you take product and cancel these e's, you get STS, UTS. So this generalizes to any expression in a Coxeter group or in a Coxeter monoid. So if you have this string of elements in S, you assign Si to this plus minus. So they come together. Then you get a singular expression which expresses the double coset. So here I wrote it just as a set, but what I mean is that it's a double coset where empty is on the left and STU, SUTS, and empty on the right. So what you get is the double coset consisting of one element, and you take the product in the Coxeter monoid. Here I took an example where you can take product in, or so it's the same product in the Coxeter group. Okay, and now I want to explain this in the picture that I drew for S3 in a different example. So we consider some paths like before associated to this subset, this string of subsets, and you have to go forward or not. So and we do it in the Coxeter complex. So what I gave for S3 was a picture of a Coxeter complex, and I'm not defining this, but I give another example, which is for this affine S3, where M was 3 for all pairs in the generating set STU. And this picture is a picture of the Coxeter complex. And now I do it by fixing what's on the left. So in this picture, you always have W empty, which is the trivial subgroup on the left, and on the right, you can have any finitary subsets. Note that here every subset except everything except STU is finitary. So when J is empty, I color them by this. So in this picture, I colored the facets where these one-dimensional ones they are colored. So they are the J here is singleton, and I use the color of U to draw this, and where two one-dimensional things intersect is where you union the J's. So when J has two elements, I circle them in gray, and then we get this picture. Okay, so we make this picture. So we label our facets in the Coxeter complex, or cells in the Coxeter complex. And now I do an example. So here is E. So we have empty. That means we have at this point, you have empty on the left and empty on the right. And you take the smallest possible coset that has empty on the left and empty on the right. That's this part. So you start here. That's where you start. And then the second entry was U. So you go to there. And in other words, you enter into the U war. And then you go to US, that's here. And then you get out of S. And there are 3 ways to get out of S. And forward means you take what goes away from the origin. So our choice is this one. So when you go in, there is one choice. When you go out, you take a forward one. And then take UT, that means you go into T, and then out U, and that's here. Okay, so this is when you have empty on the left. So in this expression, you can view them as sequence of double cosets where you have empty on the left, determined in this way. Now let's look at, so the answer to this question is a pass starting there. Now let's take something that's not empty on the left. We can take U. And I wrote some of the U, J cosets in the same way, but what I did here is that I said, so this is the original hyperplane corresponding to U. And if you multiply U on the left, it sends, for example, this to this. So this SUS actually in this picture means SUS, comma, what's here, and so on. So instead of considering this bigger set, we just remove what's in here because they are determined by what's above this line. Okay, so in this picture, we have U expression. This means you start with U, and we have U, comma, U coset. That's the smallest, and that is this one. So that's where we start. So the first step was to add S, that will get you to this place, and then you get out of S, and again when you get out, you go forward, and then you go into T, and then you go out of U to get to T. So it's yeah, the same expression as in the previous example, but where you have U on the left. And so the answer to the question, what's U expression? What does it express? It expresses a pass here. Or you can say maybe the end point of a pass here. Maybe that's a better answer. Okay, so let's now take a 2-element set on the left, S and U. And similarly to before, it's enough to now look at only this upper side of U, and also this bigger side of S. That means you are restricted to here. And the example we take, so here we start with US double coset. That's the smallest, and that is here. That's where we start. And you get out of the S, that takes you to this, and then you add T and subtract U. So the answer to the question is either a pass here or the end point of a pass here. Okay, so I gave, I think, many examples, and now I talk about the relations. So here is a quite obvious but important point, which is general about presentations. So if you have a presentation, not necessarily Coxeter presentation, but any presentation of any algebraic structure, you use associativity in a very essential way. So I think you do not have present a non-associative structure by generators and relations, because if you have one relation, it identifies one thing to another thing, but in fact you want to identify everything that contains this in the expression, and everything that contains this other side in the expression. And to do that you need exactly the associativity. And in our definition of expressions, or in the past, it wasn't clear why such thing works. So let's give an example. So let's just take some expression of length. No, I don't say length, with 9 subsets. And if you take a part of it, it's a sub expression in a literal sense here, but actually they are quite different. I mean, they are not directly related, because here you have I0 on the left and something, and I. And here you have WI3 on the left and something, and here you go from 3, 4, 5, 6. So they are they correspond to very different things. But still we can do, if you have this expressing the same parabolic double coset as JKL, and this is just this other notation, same thing written in the other notation, then you can replace this by JKL. And this is what we need before we do any kind of presentation. And this is the case, so we can now make sense of some relations, and let's start with the easy ones. The following relations hold in the between the singular expressions, and we name them. So S plus T, whatever that comes below before, is equal to plus T plus S, whatever, or the same thing that come before and also after. And we call this up. And similarly, if you take minus S minus T, wherever it happens in an expression written in this notation, you can replace it by minus s minus t and get the same parabolic double coset that is called down down. So now we have associativity and up relation, down down relation. So we will compress an expression into the following form. So if you start with Z0 and subtract, for example, S and T, it doesn't matter which order you subtract. That means you can just subtract them at the same time. And similarly for the next steps. So we can write any expression in this form where you alternate going down and going up, or subtracting and adding, or decreasing and increasing, depending on how you view it. So we write it in this form, and then it's easy to define what an expression means to be reduced. What it means for an expression to be reduced. So before we do it, I just record the regular definition of reduced expression. And now I give the definition of singular reduced expression. It's really in parallel to the regular case if you formulate it in the way I did. So we have a double coset P, and its reduced expression is an expression written in this form, and you start with I and end with J, and the requirement is that this product, so you take, so note that WK1 is the, where for any K, this is the same as, so the longest elements in Coxeter groups are involutions. They are the same, but I write as inverse. It's more instructive. So you take this product, you just take the longest element in the respective subset of S and take product, and that was what it expressed. It was also similar before, and we require that the length adds. They sum to the length of this long. So by note that this length is the length in the Coxeter group, and this was an element in the Coxeter group. And when you add the length of WK inverse, you add the negative number of the length. So we can look again that here we had product and length add, and here we have product, so that the length add. And so this definition appears in a different formulation in Jody's thesis. And also the notion of expression and this singular combinatorics is his idea from 2008. And what we write here is equivalent definition, and it needs work to show that they are equivalent, that we use in the paper. So now I just want to make sure that, so I said it's parallel, but we had some extra inverses and some extra minuses here, but it's easy to note that the definition agrees with the regular case. So record that if you have a regular expression, so this was then we assign this kind of singular expression. And then here, J and K, so the first and the middle, the small ones are empty sets, and JIs are SI. So if you take this product, you get bunch of E's and SIs. So you get W. And also, these are 0. So you only add the length is of SI. So the definition agrees with the original or the regular definition. And here is an example of a non-reduced expression. So I start with U that was here and go to empty. That's going out forward. So I don't go here because that's not forward. And then I enter T and then there. So this looks like you are going backward, but when you increase, there is one way to go. So this is the way you go, but it goes to roughly a wrong direction, and this is a non-reduced expression. You can check it using the definition also. Okay, so I want to repeat some of the things I said in the first part of the talk, maybe, and related to this singular presentation. So consider this braid relation with 3 elements on both sides. So originally it was SDS equal to TST. And if you write it in our singular notation, this is S minus S T plus T minus T and so on. So we want to get this relation from some set of other relations. I mean, we can also take this as a generating relation, but maybe we can do better. So we observe the following, that if you consider these two equivalences, the right-hand side, you have S plus T minus S minus T, and you can apply up here to relate this and this, and you can apply down here to relate the latter. So we already know these relations, up and down, and we know that this equality or this equivalence follows from this up and down we already recorded. That means we don't need to add this into our generating set. Instead, we can add these two, which are in some sense more efficient. But actually, we can do better because these relations are not in a local form. So here you have the same thing in the beginning and the same thing at the end. So by associativity or locality, why not we just identify this and this? And same for the second one. So we want to take instead these smaller relations. Here I wrote the starting point, but I think I could have written here. And this was exactly what we observed in terms of the Coxeter complex. We had this, so that the big this big thing is RR according to here, and then instead of so I think this would be SR2, but instead we can ignore this part, and that's how we get, yeah, how we get this smaller ones. And if you patch them together, we get the relation. That means they generate the relation that comes from the regular relation. And this generalizes actually. So, and so all relations that we need to identify reduced expressions come from something similar to this. So we classify these relations and call them the switchback relations. So they are of this form. So on one side, you add something and subtract something. And on the other side, you add this after subtracting something else. And here U1 and U0 need to be different. That's why they are in colors. But U0 could be the same as U2. It could be the same as UD or so on. So UI is certain sequence, which I might explain a bit more. Inside this J, which is the first set, and U0. And of course, we have this relation when it's finitary. When it's not finitary, we don't have the relation. So the switchback relations correspond to our finite Coxeter groups plus choice of this starting element. Okay, so so also this number D depend only on this where you start and the type of J. It doesn't matter which S and which W you have, and that's why we can compute these relations in all cases using the classification of finite Coxeter groups. And the theorem, analogous to Matsumoto's by Ben Elias and myself, is that they identify all reduced expressions. So this switchback together with the up and down, and we call them together as a singular braid relation.
So can you give an example of the periodic sequence in that relation?
Yes, it's the copy of the previous picture. Well, we do not need a triangle. And let's erase it and start again. So we had this T and S. And to generalize it, note that if you take J to be S comma T, you can write T as J minus S and S as J minus T. And to make it agree with the notation before, this has to be J has to be J prime. And I neutralize them into black. And I label, so this is a part of the Coxeter complex for Wj prime and J prime, where you have zero-dimensional facet or set that correspond to J prime, and one-dimensional things that correspond to co-dimension co-rank 1 subsets. So you can label it like this. And according to the notation before, this was where you start. J, setting S to be U0. J is everything minus U0. And now the left-hand side, where this is, by the way, not example, but more explanation. I can give an example after that. Maybe I don't have it on the slide. So the left-hand side, we added U0. That means we go into here, and you remove UD. And by the way, UD correspond to what lies on the same hyperplane as T. And you can obtain it by conjugating T by the longest element corresponding to J prime. And the right-hand side was this longer one. So you start with subtracting. That means you make less progress. That result in going this further way. So this is minus U1, and you add U0 back and subtract, so on and so on, add, remove, add to get there. So the last one you add was the minus 1. So I'm trying to say the switchback relation is really just the same as in the rank 2 case. And finally, I was only talking about reduced expressions, but we have non-reduced expressions, and we want to relate them to reduced expressions. And there is an obvious relation that we have. If you get out and get back in, no. That's the original place. So this is a relation that we need, and I call it stack quadratic. It's the local form of the stack quadratic relation for the Coxeter monoid. Then that's enough. So these relations identify or not necessarily reduced expressions or parabolic double coset. And in terms of presentation, we can define a category where what we have is actually the presentation. And as I mentioned, it was motivated by singular Hecke categories, whatever it is. And I don't have time to say anything about it, but there is application. Okay, thank you very much.
Thank you. So are there any questions?
I was wondering about the graph you get by moving between reduced expressions. Because the Matsumoto theorem says that is connected, and people study a lot this graph.
Yes, very early in the talk.
Yeah, and what you did with Ben is saying that this new graph is also connected. Has people study this graph combinatorially? Maybe.
Not in general. I did some examples. So this big graph for what was it, S4 is it's important in giving a presentation of the Hecke category. So in the version of Elias Williamson, that's called by them Samologikov relation. And yeah, that's why I looked into it in these smaller examples, but in general, not. But it's something that's worth looking at.
Thanks.